Okay, so welcome back to another episode of this podcast preview. This is Data Science at Home podcast, and I'm Francesco. I'm your host for the next 30 minutes. I'm very glad to have you here on the show, and in this episode, I'm going to explain some important principles that I've seen being extremely valuable for agility. And to maintain agility, but at the same time maintain consistency in software development, and more in particular with data-intensive applications. Now, the process of software development is, in fact, is an art more than a process. And it's something that has evolved in the years quite consistently. And today, it's I'm not saying it's a fashion thing, but definitely it's a trend that many are putting their eyes on, which is the concept of agility. And so having this some kind of fluid software development or agile software development, due to the fact that the business requirements are usually changing or consistently evaluated or reevaluated and reassessed once the project has been launched. And so it's not like it was in the past, these monoliths and very structured projects that could not be changed whatsoever after project launch. Today, it's much more common to see how these requirements keep reassessed. And of course, also the business logic changes, the development strategies change, the databases and the data structures that have been engineered in the first place are subject to change as well, with all the consequences that this might have in the consistency of your project, and of course the final result. Things can break if you know what I mean. Now, there is a document, a presentation, in fact, by Paul Dunn from MongoDB, which is extremely interesting, and I took inspiration from there when it comes to explaining some of the principles that I want to communicate in this episode. So let's start from the way you could find your data in a typical data-intensive application or architecture. So data can be in essentially three forms. Isolated data, we can have shared data, and we can have duplicated data. And this is so-called the data access triangle because at the three vertices, you can find one of the three, but not two, right? So you can have isolated data, and of course they cannot be shared or duplicated. Then you can have duplicated data that cannot be isolated or shared, and then shared data that of course can be isolated. Shared data cannot be isolated or duplicated. So that's why this is the triangle, because you can have only one of the three, but not two. Now, when you are in front of, for example, isolated data, there are some typical characteristics of your system that can be beneficial under certain terms and non-beneficial under others. For example, isolated data might have relatively low latency access to owned subset of the data because they're isolated. But when you try to access non-owned data, that's the problem. You're gonna break into another silo, and that means that you have to probably be speaking to different protocols or different systems in order to reach this data that is in another silo. If you are in front of shared data, you can have low latency access to large sets of data that can be updated transactionally. For example, think about an ACID transaction, like typical database transaction. In that case, you have shared data and multiple components that access your data, and presumably they will find data always in a consistent state, presumably. But of course, some of the problems, one of the major problems actually of shared data is that you have to make sure that this mechanism is actually in place. The fact that you want to maintain this data consistent across all the components that are using this shared data, it can be quite complicated. And then you have duplicated data. So duplicated data is like kind of something in between. So you have, again, low latency read access to pre-joined data, but of course you have data duplication. So if you are in a system in which you don't have, or you have storage constraints or size constraints, well, then it's a problem, because if you are duplicating data and you're duplicating gigabytes or terabytes, you understand how unfeasible this scenario might look like. I've seen actually duplicated data working pretty nicely in IoT devices. So when you have very limited edge devices, many times it is even beneficial to generate a copy of this data from two different devices rather than transferring data from one device to the other. Think about a few boards in the same room, they're measuring a temperature. They better measure the temperature instead of, they better measure the temperature in different points. It's going to be more or less the same. You're going to have a lot of duplicated data because the room, for example, is small enough for the temperature to stay the same. And so it would be quite naive to transfer the data from one device to the other, because you might be using a lot of battery, network, and of course, you don't want that. So in that case, duplicated data might actually be a good thing. Not always the case, though. So what happens now is that when you have, when you are in front of a software architecture project, usually you don't, you have a database, so like the data storage facility unit or whatever, and then you have a number of components that usually get access to this database or storage, right? And in time, these components have the tendency to increase in number, never decrease, because you might be adding additional functionality, or you might be re-engineering some components and maintaining the old ones because you want backward compatibility. You want business continuity, and so you cannot simply shut down one component. You just build on top of that, or you just build a branch from there, and you build yet a new component that still uses the same database. Now, what happens is that if you have, let's say, 1, 2, 3, 50 of these components, there is a law that says if the last component, the most recent one, wants to find data in a different schema, or wants to find fields that were not there in the first place in your data, well, it means that you have to somehow propagate or backpropagate that missing field or that new schema to all the other components that you actually developed before the most recent one. Which means that as your project becomes more and more complex, there is more and more work that you need to do. And so the more components you add on top of your architecture, the more work you need to backpropagate these changes to all the other components if you want to maintain, of course, a backward compatibility, business continuity, and all these concepts that are more related to reliability of software. And that can be a problem because the more your project grows, the more work you're giving to yourself or to your team. And to the point that that particular project might become no longer doable or feasible from an engineering perspective. That's when they invented so-called flexible data models. That is, the no SQL paradigm of database, in which you no longer have a schema that is very structured and is always fixed. And so you can be relatively flexible with your records or your documents because you might be adding new fields, removing fields, and manage the logic if these fields are present or not, depending on what component is using that particular record. Now, the question that Paul Dunn asks himself is having a flexible data model enough for software agility? And the answer to that question is a loud no. That's not sufficient. So how can we adopt a more flexible and at the same time robust approach when it comes to this type of scenarios? And so the naive observation is that you need a flexible programming language if you want to maintain that type of flexibility or have that type of flexibility in the entire architecture, which is clearly not true. And this full episode is going to be dedicated to exactly this concept. You do not need to have a programming language that is flexible in order to have or to enjoy that flexibility in the architecture. And in order to prove this, I'm going to use and refer to the most strict and statically compiled language that you might think of, which is Rust. So all these conversation, all these discussions, preamble, in fact, was to pave the way to the one concept I would like to focus on today, which is the Rust programming language. Rust programming language for data-intensive applications and, of course, flexible data models. Now, I've been dedicating a few episodes at the end of 2020 speaking about Rust, speaking about Rust and machine learning in particular. I also invited a few guests, so feel free to get these episodes on the official website, datascience@home.com, and get familiar with that language because it's, in my opinion, one of the best language, if not the best language so far for certain concepts. But of course, let me briefly explain or introduce Rust here so that this episode can be definitely self-contained. Rust is a statically compiled language. It is memory safe. It is strongly typed. It has safe concurrency. It generates native binaries, which means that there is no interpreter between the code that you generate and the machine that is going to execute that code. So there is no JVM-like or Python interpreter in between. You run on bare metal, native performance. And it's not garbage collected, which means that you have to manage your own memory. Which means that it's extremely fast. It's almost as fast as C, the C programming language. And usually we take C as a golden standard for benchmarks and performance. Now, there are some concepts, of course, I'm going to avoid to expand on those concepts, like the concept of ownership and lifetimes, that is unique to Rust and allows you to give you superpowers when it comes to concurrency and memory safety, in particular. Now, why Rust and flexible data models? Like, how can you even think of having one of the most strictly typed languages that we know and put it together even in the same presentation of a flexible data model? Well, it's because Rust comes with probably the biggest flexibility too. So it's robust, it is strictly typed, but also very, very flexible. Now, unfortunately, the followers of the podcast will not see the slide that I'm going to share. I will try to explain it as much as I can in the audio, though I will report the link of this live session in the show notes of the episode on the podcast. But it's not mandatory, of course, to look at the video. It will be just slightly easier to follow, but I will explain it as much as I can so that you can follow even by driving your car or whatever and just listening to the podcast episode. So imagine we have to represent, and I'm gonna take this example from Paul Dunn's presentation from MongoDB. Imagine we want to represent a book, right? So if you want to represent a book, we would have some fields like an ID, a title, the author of the book, the year, and the quantity eventually. Now, as you can see, or you can understand, the data types might be different, right? You can have title, author that are strings, and the year and quantity. These are usually numeric variables, so it can be integers or big integers, but probably integers is way enough for representing a year and a quantity. Okay? Now, this is the way we represent a book, from an high-level perspective. Then there is a way we want to represent the same book in Rust. And in Rust, we would use the struct concept. So we would have an object called struct book, and the fields of this struct are going to be the title and the author that are two strings, and then year and quantity that are two i32 data types, right? So far, very, very simple. Two strings, two integer 32 bits. Now what happens is when you want to insert this object into a database, what you need to do is in fact to map that data structure, so the struct, the book object, into a data type that the database understands, right? And that's exactly what the so-called mapper, it's the job of the mapper that will take these variables with a particular data type and just, map them into the space of the database, right? And so you will have a title and author as strings, and the year and the quantity as numbers, as fields indeed, numeric fields of a document, of the same document, which is the book record. Now, in MongoDB, there is a specific field might not appear in every document. And so this is the biggest problem that I want to focus on today, which is the case in which you might have fields that are optional. And so think about the field quantity. Title and author would be quite weird not to have them for some books. I've never seen a book without a title. So let's assume that there is a field called quantity that is not present for one particular book, right? It can happen. And so this means that one book or more will have a title, will have an author, will have a year, but we don't have the quantity because in the storage we just didn't collect the quantity. We didn't make an estimation, or we didn't count how many of that particular book we have in our repository. What happens then? Well, if you don't have a logic that takes into account the fact that the field quantity might not be there, that logic will break. And so that piece of software, that piece of code that is actually reading the book record without the field quantity will crash or will fail. So what happens is when you have a strictly typed language like Rust, you would have, as we said, string, i32, i32. So these are the four fields that we mentioned at the beginning of the example. And so we want to find a field quantity that is an i32. We want that. And if we don't find that, it's going to be a problem. Well, not so much for a language like Rust, because Rust comes with, this is what I mean when I said it's a very flexible language. It comes with another type, which is the option type. And so instead of having quantity being an i32, we're going to have a quantity field of type option i32. What does that mean? It means that the quantity field, when present, is an i32, but it might be absent. How flexible is that? It's extremely flexible, don't you think? So the quantity field is an optional field of type i32. And we have an explicit way of saying this via Rust. So this means that the compiler still knows that the data type of the quantity field is a well-defined type, is an option I32. So at compile time, we can make all the possible matches and all the arithmetics on the typing and pointers eventually. So the compiler can compile that and knows exactly what that type is. But at runtime, something else can happen. And Rust is very much prepared to that, which I find extremely powerful. So how do we support this optionality in code? Well, as I said, we can have, there is another notation in Rust, which is the sum keyword, sum and none. So when these fields are present, you will have some number, and when it's not, you will have a none to indicate that there might be a value. When that value is present, it will be of type I32, but pay attention, because if it's not there, you might have a none. Now there's another concept that I want to introduce you today, which is the concept of serializer, deserializer. So this is the task of, several programming languages offer this capability of serialization of objects. So when you have to transfer an object via the network or across different protocols, or even from one database to another, or from memory to a database, the very first thing that you want to do is serializing that object, which means taking the internal representation of that object and represent it as a series of bytes or bits. Then you would stream all these bytes straight to the database, and essentially you will write to the database, you will write bytes to the database. And then what happens is that on the other side, to the recipient of that object, you will deserialize that object, right? Which means that you will take all these bytes, this sequence of bytes, and reconstruct the original representation of that particular object, right? And so if you have a struct with the 4 fields, title, author, year, and quantity, you will have a series of bytes. And then, of course, you know exactly when these bytes, how these bytes are cut and split in order to represent the single variable. And then on the other side, you know where to take these splits and you just reconstruct, right? As simple as that. Now, Rust offers, in my opinion, one of the most powerful so-called SIRD mechanisms, or serialization, deserialization mechanisms. And it allows you to, the serialization, deserialization mechanism of Rust allows you to take into account fields that are mandatory and fields that are optional. And so that's probably one of the most powerful things that you can have, because if you can have optional fields, it means that fields that might be there but might be not. And if you can have a way to serialize and deserialize optional fields, you have the best of both worlds, right? Because you can be serializing everything, pretty much everything. Now, let me share again another slide right here. So in this case, for example, we are in front of the book record with the title, author, year, quantity, and another variable which is explicit, that is none. And the title and author are optional strings, which means that there is a sum and a title, sum and an author. And year and quantity are optional numeric fields. And as we can see, the representation, the mapping to the database, in this case MongoDB, is going to be, this stuff is gonna be mapped into string, numeric, and null. So the none is mapped to null, and some numeric are mapped to numeric, and some strings are mapped to strings. As simple as that. So at that point, the database knows exactly what's the type of each field, even when it's not present. It knows that it's null. So with that, you maintain consistency. So let me go now showing you how how we can annotate fields and why the SERD or serialize deserialize mechanism of Rust is extremely powerful. Again, I will show another slide here, and that's the way you can essentially inform or instruct the serializer, telling, hey, this should be a bool, for example, but it's an option bool, which means that it might not be there. And if it's not there, please serialize it as none. Now, you are basically assigning a default value to something that might not be there, and you're doing that, that replacement, every time that field is not there, indeed. So with one line of code, we have represented one of the most complex concepts in several programming languages. And that's why I think Rust is one of the most beautiful languages so far, because though in some cases it's indeed, it has a relatively complex syntax, in other cases it's extremely powerful because it has this succinct way of representing things that are semantically complex. All right. So another principle that is very interesting to pay attention to is the so-called in-place update operator. So whenever you are dealing with objects that are serializable and deserializable, and whenever you want to change these things, edit these things, you better do an in-place update. And why an in-place update is always welcome is because with in-place updates, you are taking care only of the fields that indeed require to be updated and leaving all the other fields basically untouched. And this is extremely helpful towards backward compatibility, data consistency, and also as a matter of performance. You don't have to change or remap into memory entire objects, but just the field that you are updating. So this is something that is highly encouraged as a principle, indeed. There are some frameworks, data-intensive applications that by design do quite the opposite, which is they duplicate everything. So even if you have to change something, even one field, they duplicate the entire object with that field changed. And that's not always possible, that's not always feasible, especially with data-intensive applications. So these are the essentially the concepts that I wanted to elucidate today. I, again, believe that Rust will play a very interesting role in the years to come. It's a language that is becoming more and more mature. The documentation that is available is extremely good and very, very interesting. You can basically have automatic documentation for pretty much any crate. Crate is the name of a package, the equivalent of the package in Rust. And though it's a very young language, about 10 years young or old, depending how you see things, it's a very powerful one. So I highly recommend to dedicate a part of 2021 to a beautiful language like Rust. It's going to play an important role in machine learning as well. That's my, of course, personal opinion. Time will tell. I was right when I said the same things about Python more than 20 years ago. Let's see if I'm right again. It's not a challenge. It's just that, trying to observe where the world has been and where the world is going, and just give an opinion that is, technically sound and opinionated as much as I can. I also renewed the invitation to the official Discord channel. You will find the link in the show notes or in the comments, depending how you are consuming this episode, if in the form of a video or a podcast. The official website is, as always, datascienceatom.com. You will also find all the other links to all the other social channels that we have. There is also a newsletter. that you can subscribe and get the new episodes straight to your inbox, or get informed whenever there are new posts. I will never spam you, don't worry. So feel free to reach out to datascienceatom.com and get all the links from there. And I hope to see you soon on our official Discord channel. Take care.